the only thing I want to say that when people consider a set, say, on the plane and project it, say, on lines, they are interested in basically two questions. What happens with the dimension of projection if dimension of the set is given? And it's very well understood, and it's works of classical works of many mathematicians. There is another question when you're interested in a finer thing, when you're interested in Hausdorff measure of the projection. And in this case, there is a certain critical thing. For example, if you are on the plane and you project on lines, then the most interesting situation is when your set itself on the plane has dimension 1. And then whether the projections have positive or zero Lebesgue measure on the line is a subtle question which depends on so-called Besicovitch rectifiability theorem. So on the description of a certain structure of sets of dimension 1, rectifiable or not rectifiable. So I want to say that a subtle thing. But one of the corollary of this Besicovitch thing is that if you consider a very simple set of dimension 1 on the plane, for example, you can take a square of side 1, and in each corner you take squares of side 1/4, and then you repeat this procedure to take a Cantor set, then you have this dimension 1 non-rectifiable set. So projection by the theorem of Besicovitch will have Hausdorff measure, well, just Lebesgue measure 0 for almost every line. And the interesting question was, how about quantitative Besicovitch theorem? Suppose we stop construction of the Cantor set on stage n. So we have 4 to the n small squares of size 4 to the minus n. You project this picture on almost every line, and you ask, what is the Fedor length? Fedor length is the average of the length of the projections. So by Besicovitch, it obviously should go to 0, but how? What is the rate? So it's sort of Besicovitch theorem, but with numbers. Okay. And by the way, you shouldn't look just at 1/4 Cantor set. You can take like a disk of diameter 1 and take like 3 or 5 or 4 disks of diameter 1/3, 1/4, 1/5 inside, which don't intersect, construct the Cantor set. Again, Besicovitch will say that almost every projection has length 0, but how? I mean, again, you stop at stage n, you project, you average, you get the number which depends on n, or it goes to 0. How it goes to 0? Does it depend whether we have 3 disks or 4 disks or 5 disks? Does it depend on number of this disk? Is it the same number as for the 1/4 Cantor set? Or what about this Besicovitch theorem with estimates? Well, it turns out that it's a very deep question, and it depends on many pieces of analysis, of number theory, of combinatorics, and I won't be even close to deliver the most comprehensive account of that. But I will show, just on the maybe example of 1/4 Cantor set, what kind of technique is used, and also where is the difficulty? I don't like the talks where people just present results. I like when you just show the mathematical tough bottleneck and how to go through this bottleneck. So I will try to show it. Unfortunately, it will require some formulas. Okay, so now I'm skipping all this Hausdorff dimension and let me explain one thing. So, so if you have any picture like this, so let me draw like 3 guys, and it should be dimension 1, so they're of the size 1/3. in the disk of diameter 1, it's very easy to prove that if you go up to the stage n, constructing this Cantor set, then the Fedor length of this picture will be bigger than C divided by n. So it's proved in several papers of Perti-Mattila. It's not very difficult, some energy estimates. Okay, so it turns out that if you consider 1/4 Cantor set, this estimate can be improved. Okay, so in this case, by the way, why Fedor needle? It's Fedor needle landing near Cantor set. On which distance? Constant to the minus n. Okay, so delta is exponential in n. Okay, so in this situation, if you make nth stage Cantor set, you will have another answer, better. So how sharp, we don't know, but it's a better answer than for general picture. And we got it with Michael Bateman, and it has a relation with the solution of Stein's problem about the maximal function in Cantor directions. Anyway, so I don't have time to stop on that. I will just go by. So here is the, probably I get the proof of this result, but we don't need it. We don't have time. So we skip all that. So then there is another thing which I want to mention, just spending 10 seconds, when you consider random Cantor sets. So there are many, many interesting models of randomness. Again, you should construct this Cantor set, random one, such that dimension would be 1. So for example, you put these disks somehow, one randomness that you rotate them, and then another randomness that inside you also rotate independently, etc. So there are many, many different models of randomness. And it somehow fantastically happens that the expectation matches the very simple estimate from below. Okay, in all models of randomness, it doesn't say that for all of them, but for all model of randomness I know, and there are several of them, this result holds, same thing. So constant divided by n. So this guy is very special, right? It's worse than random. Okay, so now we start to work with this guy. So on the stage, say n plus 1, we have 4 to the n plus 1 small squares, and these are x and y coordinates of these squares, where epsilon plus minus 1 and epsilon prime is also plus minus 1. So when you project, you will get these points. And of course, you can forget about cosine theta, just divide by it. It's a simple dilation. And so you can think that the projections have landed, the projection of centers landed at these points, where again, epsilon k plus 1 run out over plus minus 1. And t is a parameter, which is also runs, but say between 0 and 1. So these points are the support of this convolution of delta measures. And if we take the convolution of these delta measures and convolve with a small characteristic function of small interval, you may think that this is a certain function, right, which is very important, but we are not interested in this function. We're interested in its support. So support is exactly, the support of this function is exactly the projection, not exactly, but practically the same as the projection of our Cantor set on direction t. And so we're interested in the length of this guy and then average over t. Okay, so function itself is not so interesting. Its support is interesting. Now, still, we will use this function a lot. And of course, Plancherel will be used, but much more than Plancherel. And so this is the Fourier transform of this function. And you can notice immediately that we somehow, important thing appeared here, a certain trigonometric polynomial, which depends on n, because n is the stage where we stop, and its frequencies are dictated by the geometry of the Cantor set. Okay, so here is our main result, which we obtained with Yuval and Fedor Nazarov long ago. So it says that Favart length of this thing for 1/4 Cantor set is basically n to the power minus 1/6, less or equal than n to the power minus 1/6. We actually cannot prove minus 1/6. We can prove minus 1/7 or anything which is smaller than minus 1/6. So if you remember, the estimate from below is this, and so they're very far apart. But we cannot do anything else. But I would say that this is a very good result still, because the previous results were like this. So this is Peris and Solomiak and Terry Tao. So separate papers. The previous estimate was that Favart length of the nth iteration of 1/4 Cantor set will be estimated like exponent of minus logarithm star n. So what is logarithm star? It's a very bad function. You take your n and many, many logarithms and look at this change of logarithms. First time the log drops below 1. You count how many logs you need, and this is logarithm star. So let's call this estimate power estimate or polynomial estimate. And this estimate is much worse than this. So you can take as many logarithms as you want, and this estimate will be still worse than that. So it's super far from power estimate. And in principle, we will be chasing the power estimates. And let me confess that it's not true that we can always get them. But for this case, we can. Okay, so again, this is the function. This is this convolution. So we need this length. We need this average length, where L is support of the function. And now I start to introduce sort of combinatorics of the proof. But I really want to come to a certain stage. Maybe it's now slide 5 or 4, like maybe slide 19, to come to the real difficulty. Because for a while, we won't even see what is the difficulty. But still, combinatorics starts here. So we fix a certain large capital N. We fix a certain number, which is basically n to some small absolute power. We consider for these functions, which we defined above, a certain maximal function. And then we split the directions T to 2 classes. So this is the class of directions which we will call good directions. And the rest of them we will call singular directions. And why this is good? Because it says that, what does it mean this function ftn is large? For example, what does it mean that this L infinity norm is large? It means that at a certain point, many small squares pile over this point. It's basically exactly definition of F. So that's a well-deserved name, good direction, because it means that if this is direction T, then there is some point some point is set here, L infinity is large, such that many squares will be piling over this. And that's a good direction because basically you should understand that we will be using self-similarity a lot. If this happens in this scale, then it will repeat itself in smaller and smaller scales. And I will formulate soon that actually good directions are really good. But then there are also singular directions. And the main difficulty will be to prove that the Lebesgue measure of singular directions is small. And that's the most difficult part of the proof. But in fact, we can do even so the next definition is even more important. So there are super good directions. So they're inside the good directions. It means that you don't have just one point, but you have many, like you know what is the measure of the points or which do you pile up, right? So for example, super good directions are those where this, for certain n, you have, well, anyway, your maximal function is bigger than k on certain large measure, not very large because k is itself large. So 1 over k cube is not very large, but still on a certain fixed amount of measure, you have this piling up. So these are definitely super good. And then, of course, we have quasi-singular where it's not super good. And so quasi-singular, they're much bigger set than singular, and it will be much more difficult to prove that its Lebesgue measure is small. Okay. Now, that's the kind of easy and nice theorem, which I, of course, not prove at all, but will explain. So we fixed a certain capital N and did everything around this capital N. And suppose we have this direction which is good, enumerated by this n. It turns out that you cannot say that projection at this scale are small, average projection. But if you wait, don't do it at n, but wait exponential time. And then projection will be small. Remember that k is some n to small power. And so changing the variable, you will get that we proved a certain improvement of Paris and Salamiak. We will prove that Fedor Kn is less than constant log n to some small power, which is still not the power estimate, but from here we got something much better than before. So and the moral is that if you have good directions, you wait a little bit more, and you will be done. So the projection will be small. About super good direction, it's much better. You don't need to wait exponential time. You need to wait. Basically, it's almost like equal to n. You need to wait a little bit more. Again, let me remind you that k is n to some small power. So so it's like n to the power 1 plus epsilon, and again you get a small projection. Okay, so this is the role of good and super good directions, and especially this one is good because from here we will get the power estimate. Already, if we prove that the number of super good directions has small measure. Okay, so so here is like main theories. So the first one is simpler, the second one is much more difficult. So the simpler is that the Lebesgue measure of singular directions is small. Again, k is n to the small power. And this is the definition of singular directions. where quasi-singular directions are not defined in terms of the norm of Tn, any norm. They're defined somehow, I don't want to remind you, but it has nothing to do with norm. Singular directions are defined in terms of norm, quasi-singular are not. But it turns out that there is a theorem which is very helpful and sounds nice. So if you have a quasi-singular direction, definition is this, then the same thing happens, but you should replace L infinity norm by L2 norm. So singular from quasi-singular, basically, the difference is that you choose different norms. And this is a difficult theorem. That's a combinatorial thing. And to finish, we need to prove the following theorem, that the measure of directions where the maximum of L2 norms is small itself. So after that, power estimate is proved. Okay, so I really want to come to the difficulty, because if I really explain the difficulty, it will become really very fun to see what happens. Okay, how proof is organized? So first of all, here is a quasi-singular direction. We suppose that we already proved that quasi-singular means that L2 norm is small. And so, okay. So we use, of course, Plancherel, we get something like that. So we get something like this, which is already just in terms of convolution of these point measures. Okay, and convolution of the point measures is a certain trigonometric polynomial. So because this integral is kind of bounded by something, we just split it into, as usually we do, like with geometric progression. So we do it like that. It's and this becomes a trivial corollary of this. Okay, so we now should take a look at one of these integrals. And when we take a look at one of these integrals, we come to consideration of such trigonometric polynomial. So this n here is dictated by this n here. And this inequality becomes that inequality. It's just a change of variable. So we have a certain estimate from above for this type of trigonometric polynomial. There are n terms, not terms, but factors. There is a certain m, which we have no idea what it is, but basically I think it will be something like logarithm n in the future, because here m was parameter, we were free to choose it. And this is the estimate we get from above. And the rest is the estimate from below, which will come to contradiction with this estimate from above if the measure of t super, not super good, but quasi-singular is large. So under this condition, this estimate will come to contradiction to the estimate from below, which we're going to give. Okay, so what is this estimate from below? So first of all, in this polynomial, we have high frequency and low frequency. So when 1, I forgot to change it, it should be 1 is low, 2 is high. And what is low and high? So we have this mysterious m, which is supposed to be, I guess, something like log n in the future. And low frequency are those, and high frequency are those. They're, of course, high because 4 to the L becomes very large. And the proof of the estimate from below splits to several pieces, and only one piece will be the core, like the most important stuff on which everything is hinged. So first we estimate this high frequency from below. Now, this is an easy task, but notice that for us, it's very important that we do it on this interval and not on this interval. So it's not from 0 to 1, but it's 4 to the m to 1, 4 to the minus m to 1. And why it's important? Because if you look at this polynomial, you can easily see that it's concentrated near 0. And so if you would estimate from 0 to 1, it would be immediate. But because you don't, you need to work a little bit. And I will stop explaining at this moment. Now, so we estimate the high frequency on this interval from below. And then that's coming to the punchline. The thing is that we don't need to estimate of this guy from below. We need to plug in P1 squared as well. But P1 squared can spoil the estimate because this P1 has lots and lots of zeros. And not only zeros, but something around zeros where P1 is small. So let's call it set of small values of low frequency. So we sort of, in fact, need to estimate this stuff, P2, not on 4 minus 1 to 1, but on this perforated place. So minus set of small values. How to do that? We need to estimate from below on the red. So how? We estimate from above on the blue. So we estimate this high frequency on this blue, on set of small values from above, and then subtract. And then we have estimate on the perforated set. On the perforated set, we can add P1 here inside, because on the red, P1 is bounded away from 0. And so after all this work, we will have the estimate of what we need, the whole polynomial, low and high, on the interval 4 to the minus m to 1. And let's hope that it will contradict the estimate from above is the set of quasi-singular direction is small, is big, is big. Yeah. Okay, so the main word was already pronounced. So this is the set of small values. So it rules everything. So it's a set of small values of a low frequency polynomial. So now I carry out this program and I will skip almost everything. So here is the estimate of this solid interval without perforation. It's not trivial, as I said, because most of its mass is near 0, but it's not very difficult either. It uses some complex analysis, Carlson measures, so it's not totally trivial, but quite okay. Now we need to come to this SSV, set of small values of low frequency. Well, it's an absolutely concrete polynomial. So this is our guy. This is the polynomial of low frequency, which can be written in this form. And so we multiply all kind of cosines here, and we use this trivial formula. We see that this low frequency polynomial is actually bounded from below by something like that, by very simple expression, algebraic expression, one sign, another sign. And we can always look what are zeros of these signs and what are the set of small values. By the way, what is small value is where this guy will be smaller than, I don't know, e to the sum am, and a we choose whatever we want, like 10 maybe. And so it means that these signs should be, one of them should be smaller than e to the some big constant times m. And of course, we understand how it looks like. These are zeros of these two signs and small intervals, and they become smaller and smaller if a becomes large. But the main thing that the number of intervals doesn't depend on a. So it's like you have a fixed number of nails, and it doesn't depend on how small you want your set be. What does it mean? You set of small values, you set a certain constant smallness. But so it should be that it doesn't depend on the smallness. So only these intervals start to depend on the smallness, but not the places where they're attached to. And this is the main beauty and sort of present to us, that this is what happens. This set of small values has the structure of the set of small values of low frequency. By the way, in any other picture, not necessarily 1/4, you will have the same thing. You will have trigonometric polynomial. It will be maybe more complicated than this one, but you will always be able to split it to low frequency and high frequency by some secret mystery m. And you can always ask about a set of small values. You always try to analyze. You can try to repeat all this. And just saying that it's all looks very familiar as soon as you do it one time. Okay, so this structure of the set of small values somehow is very important for us to make this estimate from below, which of course I will, all these calculations I will skip. And finally, we come to contradiction with the estimate from above. So this is estimate from below, this is estimate from above. And so if we choose such n, and then we come to then we prove that the set of quasi-singular directions has small measure. So I fortunately gave you a certain idea what is the main mechanism. So there are many mechanisms, but the main mechanism is that when you project this self-similar stuff on any line, you will have a certain convolution of delta measures. When you take the Fourier transform, it becomes the product of trigonometric polynomials, which sort of nested into each other. And then you split this trigonometric polynomial to two parts. You should do it correctly. And look at the set of small values of the low frequency part. And if it has this nice property that it's sort of nailed to say e to the some fixed constant times m places, and when you make smallness like this, the intervals around that becomes e to the minus bm, where b grows with a. Then you are done. You will have power estimate. So here is the definition of this property of set of small values. Let's read it. So we say, yeah. So we have a certain function phi, which is trigonometric polynomial, and then we consider phi of x, phi L of x, phi L squared of x. This is what I mean by nesting phi L to the m of x. These are all trigonometric polynomials, higher and higher degree. And then you look at this product and you look at where it is smaller than psi-m. And psi-m is something like, for example, it's exponential. So we say that this phi has SSV property if the set of x's satisfying this thing is contained in this number of the intervals of this small size. And C2 shouldn't depend on C1. And C3 should depend on C1. Okay, so if we put here exponent, that's what we just had. It's a set of small values of the simplest type. Now you can, maybe you don't have this property with just exponent, even with very large C1. So maybe you should put a much smaller guy to get the same structure. So suppose you put this smallness much worse than exponent, like this. And again, you want the same number of intervals with the same size of intervals. And again, if C1 is large, C2 shouldn't change and C3 should become large. So then we say that phi has log SSV property. And finally, if we put even smaller smallness and get the same type of structure, then we say that we have a square SSV property. So what we saw above was L equals 4, phi some trivial trigonometric polynomial, some couple of cosines, and we had this first property. Now, if you consider absolutely any picture, but self-similar, like this, again, it should be dimension 1, or like this. So when you have 3 or 4 disks, so this L is 3 or 4, it turns out that you can always prove SSV, the best SSV, exponential SSV. No, it's called here just SSV. So for them, there is always SSV, and so there is always a power estimate. Here is even the proof, which of course I will skip for L equals 4. And here what happens when L equals 5. So you can draw a very special picture. So 5 disks are inside the disk of diameter 1, each of diameter 1/5. And here I even indicated their coordinates. So, so the coordinates of the centers. So you choose these coordinates of the centers. So your phi will become this trigonometric stuff. remember that you should put inside Xi, 5 Xi, then 25 Xi, then 125 Xi, and then multiply everything. So this is low frequency guy. And you look at the set of small values, and it turns out that it doesn't have this property. It just no way. It just doesn't have it. It is very simple calculation. Not difficult at all. So we cannot use for this picture, we cannot prove the power estimate just because this obstacle. And this happens because this guy will have recurring zero. So we have this huge product will have a huge multiplicity of zero at one point. So algebra is given in such a way that you just cannot do anything. Moreover, it's not just one direction. Here we projected just on one direction and it didn't have SSV property. But it turns out you can project on many, many directions and you will not have SSV property. So the proof above just breaks down completely. And this is just for some algebra of disks. And 5 of them. So we very slowly coming to the most interesting part of this research, which is actually related to many, many things, and mostly to algebra and number theory. And I won't be able to explain many of these, but I will explain at least what was the real problem with this example. So what was the real problem with this example? So we'll look again at this phi naught. And we just change variable in this 5-term trigonometric polynomial. And we see that we are working with this algebraic polynomial. So this e to the power, whatever you explain, you denote by x. And the powers of this algebraic polynomials will be 0, x to the power 0, 3, 4, 8, and 9. And so our previous phi naught is just this guy. And this thing that at 1 it is 0, and then it will accumulate zeros when we multiply, is that this thing is the root of this polynomial. It turns out that it means that this polynomial with 5 terms is divisible by the 12th cyclotomic polynomial. So this 12 here, where is 12? This 12 here says us that we should look at the 12th cyclotomic polynomial. And it turns out, so what are cyclotomic polynomials? Well, maybe I don't want to explain it, but these are irreducible polynomials with zeros which are roots of unity. And so yeah, I even wrote some of these cyclotomic polynomials here. So this is phi 1, phi 2, phi 3, phi 9, phi 30. You see, they all have coefficients plus or minus 1. So for a while, people even thought they always have coefficients plus or minus 1. But phi 105 has the first one, which has coefficient minus 2. Anyway, so we have that phi 12 divides our A. And the most important thing for recurrence of 0, that we always hit 0 when we put into A this L squared, L cubed, etc., is this fact that the number of terms and the cyclotomicity number are mutually prime. So that was the real reason why we have this difficulty with a set of small values. So that's, by the way, actually another definition of cyclotomic polynomials. So anytime we will have phenomial which appeared from our picture, from our geometric picture, and it will have a root of cyclotomic polynomial of order, or a root of order S of some cyclotomic polynomial, and we have this mutually prime thing, we will have the same difficulty. So maybe I should sort of stop explaining things and start to formulate some results. So many of this Cantor set, including one quarter Cantor set, can be described algebraically in terms of algebraic polynomial. So these are sort of rational product Cantor set. So what is rational product Cantor set? Oof. So what is rational product Cantor set? We take number L, which is the product of two integers bigger than 2, and we divide each side of the square by this L, which is L1, L2. And then, roughly speaking, I won't explain it more than that. You choose like L2 guys from here and L1 guys from here, and you just take the Descartes product of each of them, each from this L2 and each of this L1, you will have small squares in this unit square, and each side will be 1 over L. And that's more general example than one quarter Cantor set, but sort of the same type. And then you can make it algebraically like that. You consider two polynomials. So like this. Because what is A? I said you choose L2 guys from here. So they're enumerated 1, 2, 3, actually 0, 1, 2, 3. And so this will be our B's. And the same with A's. So now we have phi, which will be this guy. You see, it depends on direction. And the estimate of the Buffon needle probability will depend on the algebra of this polynomial, of these phenomials. So let me formulate a couple of theorems and we'll stop. So first of all, we'll look at the roots of these polynomials of this type. Let's call it a rational root. They shouldn't be rational, by the way. They can be the root of the type e to the I theta naught, where theta is irrational, and this one should be considered two. And so, but it should be considered separately. So if all roots of A and B sitting on the unit circle have this form, so here I just said that K and S are mutually prime, which goes without saying. But if at the same time they are not mutually prime with L, then SSV property holds, and it's exactly like in the one quarter Cantor set, and we have power estimate. So if we avoid the enemy which was shown on the example above, we have a power estimate. Now, if we have a rational root, either a rational root or the good rational roots. Good is like they're like here. So then we don't have power estimate, we have this estimate. we don't know, maybe we do have power estimate, but I doubt that. And we have this slightly worse than power estimate, right? This log n in the denominator shows that it's slightly worse than this. Now, I have to pronounce this result theorem about irrational phase roots is based on this famous result of Baker, for which he got Salem Prize. Or not Salem Prize, Fields Prize. Okay, so now, so we have like good cyclotomic devices, and suppose we have bad cyclotomic devices. So we have a rational root with rational phase, but these guys are mutually prior. So if only one such bad root happens, we again have the same result as in the previous theorem. And if we don't have irrational phase roots, it's even better. So you allow to have one bad cyclotomic root. Next theorem says that, what about general? Suppose the very bad cyclotomic root all the time, not one, many of them. What, can we have any estimate? Well, yes, instead of n to the minus p, which we don't have, or even this, which is almost like n to the p, we instead we have this, but it's completely universal. Okay, and finally, I want to formulate one funny theorem, which has a combinatorial proof. So suppose this polynomials, these phenomials are not very large. Well, no, they can be very large. You see, it doesn't say anything about powers of these polynomials. So the largest integer in this set A can be billions. But what we care about is the cardinality of how many powers you have. So this is why we should call them phenomials. So we have, if A and B are phenomials with very few terms, like this, then this log SSV always happens, and we again have this surrogate power estimate. And if no irrational phase exists, then we have even power estimate.